Okay, let's move on to physical and chemical properties of carbonyl compounds. So carbon has a value of 2.55 on the Pauling electronegativity scale, and oxygen a value of 3.44. This leads to the presence of a permanent dipole, and you're used to representing that in school with a delta positive symbol and a delta negative symbol. It's also sometimes useful to think about it in terms of the molecular orbital between the carbon and the oxygen, which in this case is distorted over towards the oxygen like that. This permanent dipole influences the properties of carbonyl compounds, both the chemical and the physical properties. So the first question here is, how does a dipole affect the physical properties of a compound? How would you expect a compound with a carbonyl group to be physically different from an alkane with a similar molecular weight? So the important parts of this question are talking about the dipole and also how it affects the physical properties. So our strategy for answering these questions is to state the strongest type of intermolecular force between the molecules in both cases and then to compare them. So we start with the carbonyl, and in this case the strongest intermolecular force is going to be permanent dipole, permanent dipole. And then we need to think about the alkane. So since alkanes are compounds only of carbon and hydrogen, and the electronegativity difference between those is quite small, the strongest intermolecular force is going to be van der Waals. And we also talk about similar molecular weight, so the number of carbons will be similar as well. And then we need to state the comparison between them. So in this case, permanent dipole, permanent dipole. So we also need to compare these intermolecular forces, and in this case the permanent dipole is stronger than the van der Waals. So what is the consequence for this in terms of physical properties? It's likely that the carbonyl will have a higher boiling point and therefore is more likely to be a liquid at room temperature. Compared to the alkane. Okay, so the next question is to do with the chemical properties. Permanent dipole also affects the chemical properties of carbonyl compounds. Their chemistry is dictated by the delta positive and delta negative regions of the dipole. What general class of reactant will a carbonyl group react with, and can you give some examples of these? So it's asking for a general class initially. It's not asking for anything specific to start with. So general class of reactant. So in this case, you have delta positive and a delta negative region. We'll just draw those on. Okay, so this delta positive region here is able to attract a specific class called a nucleophile. Okay, so nucleophile is the general class of reactants. And then some examples of these. So which kind of molecules make up nucleophiles? We can have electron-rich molecules. So that can be things with a lone pair, for example ammonia. Lone pair here. And also negative ions. So in this case something like the cyanide ion. And the lone pair is here on the carbon. And the second question, would you expect carbonyl compounds to be soluble or miscible in water? So to answer this question you really need to think about water, and water is a significantly polar molecule. If you remember from when you were lower down the school, it has significant areas of positive and negative charge. The negative charge on the oxygen near the lone pairs and the positive charge on the hydrogen. And in order for something to be soluble or miscible, it needs to have some kind of attraction for the dipole that exists in water. So carbonyl compounds have a dipole. And therefore they are likely to be attracted to the delta positive and delta negative areas of water. This attraction is going to depend specifically on the carbonyl, so the best answer to this would be that you will have variable solubility. Some carbonyl groups are significantly soluble, such as the carboxylic acid group is particularly soluble. So last question, as you ascend a homologous series of a particular class of carbonyl group, the boiling points of the compounds increase. Why? This isn't actually very much linked to your understanding of carbonyl groups. It's trying to bring you back to some chemistry you've previously learned. So there's a few words that you need to be able to understand here. The first one being homologous series. What does that mean? And what does boiling point, what part of chemistry is your boiling point being linked to? So in the first case, you need to think homologous series. So that's a group of compounds, group of molecules, which have the same functional group but differ from each other by the addition of CH2 groups. In this case, it's actually not asking for a particular carbonyl. It's not told you aldehydes or ketones. So that can give you a little bit of a clue about the kind of question that they're asking. Let's just have a think about a homologous series of aldehydes. So this is a homologous series of aldehydes, starting from the top one, methylaldehyde or methanol. And we've got an addition of a CH2 in each case. And since it's asking us about boiling points, it must be asking us about intermolecular forces. Now our strongest intermolecular force here is going to be the dipole-dipole, but in this case we've got no change in dipole-dipole forces as we go through the homologous series because we still have the same functional group present and there aren't any more functional groups present. So it must be to do with the alkyl groups that are present as well. So having a look here, the presence of these alkyl groups means that the van der Waals forces is changing. Okay, so we are. Okay, so as we go down the homologous series, we've got an increase in the number of atoms. So addition of CH2s going down the series. Means there are more atoms and therefore more electrons present. This leads to an increase in the strength of van der Waals forces between the molecules. Higher strength means that more energy is needed to overcome.